All right, guys. Good afternoon, everyone. I gave you all your exams. I'm going to be posting the exam key in on Canvas, so you can take a look at the right answers over there. I don't know if you have any question at this point that you would like to share with everyone. No? If not, then just let me know. Just check your exam. Make sure all points add up correctly. And if you have any questions, just let me know. Okay? All right. So let's continue with the contents of the class. So we finished talking about pore-elasticity. We know how to solve problems in linear elasticity. We know how to solve problems now with pore-elasticity. And now we're going to start talking about some other types of loadings that can be applied to porous solids. And we're going to start talking about thermo-elasticity. We know that we can also apply changes of temperature that are going to result in strains. By now we know that strains combined with some constrained displacements are going to cause stresses. So there are several applications for thermoelasticity, and probably the most obvious one is where you have very large changes of temperature are going to be on geothermal energy. There are two types of geothermal energy harvesting. One is shallow geothermal, and most of those involve, for example, the same foundations or building or houses where you will circulate the fluid that will pick up the temperature of the foundation, which is surrounded by rock or by soil, and you will adapt the temperature to cool it down in the summer or to heat it up during the winter. And that's mostly used for residential purposes. There is also deep geothermal energy, and the concept on deep geothermal energy is to have very deep wellbores that go into zones where the temperature is very high, many times close to regions where the magma is not far, and you will inject water, recover steam, and with that steam run a turbine that generates energy. Right now, this is something that is starting to pick up more and more momentum, and sometime it might replace quite a bit of the energy that we consume today for electricity. For example, I know about the project right now being deployed, I think it's in Montana or North Dakota, I don't remember, in which they are drilling wellbores into a deep mine in order to inject cold water and then circulate that from. This is actually very interesting because they inject from a wellbore in which they do hydraulic fractures, and they collect it from another wellbore in which you also have hydraulic fractures to make the water circulate through these two hydraulically fractured wellbores in order to collect the water and receive it back. One of the issues with geothermal energy is that you'll do that mostly in granite, and if you don't have any fractures, your hydraulic conductivity is very, very low. So you want to enhance somehow that conductivity in order to make the water circulate, but not too much, because otherwise it will go by very quickly and it wouldn't pick up any heat from the rock. But you know, I think there's in the future probably a significant part of demand may be covered by geothermal energy. Less fancy, but very important too, it's drilling of a wellbore. Many times when you drill a wellbore, you use drilling mud, which is on surface pools, and it's a surface temperature, so that when you inject it and it goes very deep, it's usually at a lower temperature than the formation itself. And because of that, by circulating cold fluids through the wellbore, you can lower the temperature of the rock, and if you lower the temperature of the rock, you will cause shrinkage in the rock too. That's going to lead to tensile stresses. We're going to see later on, I forgot to say this, that the problem with drilling is that you generate a tensile hoop stresses, theta theta. And when you have geothermal energy by injecting fluids, you usually increase shear respect to normal stress. We're going to see that why later on in a little bit. And there are some other applications related to thermo-elasticity too, and those involve fluid injection. So in this case is fluid injection too, but I wanted to put it separately from geothermal energy. There are some applications in petroleum engineering in which you inject water. You may inject CO2, or you may inject also some other chemicals, like for example foams, polymers, all kinds of injectants that can cause changes of temperature are going to be important. There are two types of fluid injection that you could do. You could either inject just water, for example, for water flooding, and usually that water is going to be liquid. But there are some applications too in which, especially for heavy oil, you want to inject steam. And imagine if you inject steam, you're injecting very hot water. So you're heating up the rock much more than what it is usually its temperature. This is an application which is very common in heavy oils that are contained in sands. And mostly those sands are shallow. There are many of these deposits in Canada that they're called tar sands, and one solution is to mine them, but mining of tar sands is not very environmentally friendly. So another solution is just to recover this shallow heavy oil by circulating steam from these sands. And there you can change the temperature quite a bit. What would happen, and we're not going to go into this example, but I like to mention this. What would happen if you inject a lot the temperature in a heavy oil reservoir? And you're injecting steam, and at the same time you're heating up the fluids. And let's imagine that the volume change is negligible. Okay. Super critical, you mean the fluid? You're talking about phase behavior or about the disadvantages of doing that? Phase behavior, okay. Yeah. But notice that you're increasing the pressure because you're injecting a fluid, but also if you heat up the resident fluids, they're going to try to expand to some oils, may change phase to and go into a vapor phase, and that's going to cause a lot of pore pressure increase. There are some cases that are documented in which they have geysers on the surface because of not controlling well the pore pressure, so they will create outbursts of vapor on the surface. Of course, you don't want to do that, right? And that's something that you have to control in these cases. But that will be an example of undrained loading. You heat up everything, and if it's undrained, you will create increase of pore pressure because of the heating up the fluids and making them change phase. And the last example here that we're going to talk about, and all the concepts that we're going to see in a bit also apply in the same way, just have to change them a little bit, will be hydraulic fracturing. There are two hypotheses here of how change of temperature could affect hydraulic fracturing. The first one, it's there are some people that support that you could decrease the temperatures by, for example, injecting liquid nitrogen. And if we were to inject liquid nitrogen at very low temperature, I don't know, what is the temperature of liquid nitrogen? I don't know that number. But it's like, minus 100 C, 150 C, something crazy. So the idea here is that you inject liquid nitrogen and that cools down the rock very quickly so that the rock shrinks. And as it shrinks, you create tensile stresses that help hydraulic fracture propagation and hydraulic fracture branching. Conceptually, that kind of makes sense, right? Conceptually, I don't know. Practically, it might not be, as easy as one may think. But conceptually, it kind of makes sense. So you lower the temperature, create lots of tensile stresses so that you have a hydraulic fracture, or, we're going to talk about this later on. In general, or more scientifically, these are called fluid-driven fractures because the fluid is opening the fracture. Well, in this case, you may have fractures that are not opened by the fluid, but are just opened because of the temperature. And there are some other people that argue that you could heat up formations, for example, by getting downhole a microwave tool that will send microwaves and heat up the rock. And in that way, in theory, you could heat up a porous medium. There are actually experiments like this. So imagine that you put a piece of rock saturated with water in the microwave. And you put 1 minute there, full energy. What do you think is going to happen? Is it rock saturated with? Actually, we should bring a microwave here and run that test. What do you think is going to happen with that rock? It's a pore elasticity problem, okay? So probably there is more than one solution, right?
Would you consider it drained or undrained?
You're getting into the right direction.
Out in time, are we going to get a puff of steam coming up?
Okay.
Or are we just going to have increasing stresses in the rock? Or a combination of both, probably?
Well, there are these people from Aramco Services that have run this test in which, and there are also other people that did this before, that if you take a rock saturated with water, you put it in a microwave, and then you heat it up, if the permeability is high, as you, Robert, said, so high permeability, yes. And you're just going to create a steam that it just gets out of the pores and does nothing to the rock, which will correspond to what type of loading? It will be drained, right? But if you have a low permeability so that when the fluid is expanding and the vapor is expanding and it doesn't have time to escape because permeability is very low, what you can cause is you can cause cracking of the rock. And that cracking is actually going to break the rock in quite a bit. So here you also generate steam, but is undrained loading, and it leads to cracking of the rock. And under this concept, some people think that if you heat up formations underneath in the subsurface, you can also create cracks in the subsurface. I'm not sure about that. I think it's you.
You'd have to overcome the confining stress.
Very good point.
Because if you throw like sandstone that's wet in a fire, it'll blow up.
Yeah.
It's because it doesn't have anything holding it.
Exactly. So in this case, in the microwave too, if you see, it's just like a rock without any constraints, any confining stress or any rock next to the sides. So we know that those boundary conditions are not realistic in the subsurface. If you had this rock under confining pressure or confining stress with more rock to the sides, you could still create some of those fractures, but you will have to go into the mechanics of fluid-driven fractures in order to have something like that. But it's not going to break in 1,000 pieces as it would on surface. But all of this is related to temperature and changes of temperature, how they can affect rocks. And so I like that we go through the theory of how we deal with these changes of temperature to incorporate that into elasticity first and then into thermo-elasticity later. First of all, let's try to consider a more, this, I know this is something that you know, but I want to get into an agreement here of the signs that we're going to use. So if we increase the temperature of a solid, what are we going to have? We're going to have dilation, right? It's going to expand. And we're going to assume that this is an isotropic solid. And you're going to see why in a bit, why this is an important assumption. If we cool down the same solid, that's going to shrink, okay? And this is going to be a volumetric strain, which is going to be negative. It's going to be a dilation. Remember that dilation, we want to consider dilation is negative, and this is going to be a change of volumetric strain, which is going to be positive. It's going to be a contraction. So what about this is a volumetric strain. What about shear strains? Can you cause shear strains by changing temperature?
If there's existing fractures, and like, so if there was like a angled fracture through the rock and the pieces were expanding in different ways, you might cause.
Okay, so I think you're getting into uneven fields of temperature, right? Well, now let's assume that the field of temperature is homogeneous everywhere. So what do you say? Yes or no?
If temperature is homogeneous, there's no temperature gradient?
Well, no, there is no temperature gradient in space, but it's temperature gradient with time. Okay? So you think you're going to have shear strains or no? Well, there are going to be no shear strains as long as you have an isotropic homogeneous solid. Because if the material properties are the same everywhere, they should shrink or dilate the same, and there is no reason for having a shear strain. But this is going to be different from a heterogeneous solid. Imagine that you have a solid like a rock, and most rocks that are layered with materials inside with different thermal conductivity or with different dilation coefficient. If you were to say this one shrinks more than this one, if you were to deform this under no constraints, it will shrink like that, right? And very likely you will have a lot of shear strain in the interfaces. So for isotropic solid, we can assume that. But if you have an anisotropic heterogeneous solid, it gets a little bit more complicated. Yes, Preston?
So if it was a localized increase in temperature,
Yes.
even though if it's isotropic, can you create shear strains?
You could, yeah.
Okay.
Yeah. But when you consider a point, a local point, that would not be the case.
Just a little question about notation. Is it delta strain or just strain?
This is delta. But so the change of volumetric strain.
So the change in strain, not just strain of the cell.
If you consider that the initial strain is 0, or there is no strain at the beginning, then it will be the same.
So it's the same thing.
Yeah. All right. So with this assumption of an isotropic solid, then now we can modify our equation of linear elasticity. So we knew that stresses are proportional to strains through this constitutive equation. And what we're going to do now is we're going to modify our constitutive equation to incorporate the changes in temperature. So, and this is going to be going to depend on here two coefficients. Because this is an isotropic rock, we're going to consider that the change is the same in all directions. That's why we have this identity matrix here. This is a change of temperature. Here, this is going to be the bulk modulus. And also, notice this one it's invoking two things, isotropic, and also it's invoking the fact that there are no shear strains. And here, this is going to be the linear expansion coefficient.
Is it the same as the thermodynamic? It's constant pressure?
The linear expansion coefficient?
Yeah,
Yes.
This is thermodynamic beta, so 1 over
Yeah.
V.
Yeah, it's the same thing. But now we're putting it into the context of linear elasticity in 3 dimensions. So let's go to a case in which we just have dilation. If we have dilation, what are the boundary conditions? What is going to be the stress, the total stress in the solid? I forgot to say something here. I'm not going to put pore pressure right now, just to make this story easier, okay? So we're just talking about thermoelasticity with no pore pressure. So sigma or S is the same. Okay, so then what is going to be the stress if I just have a dilation case of an unjacketed rock without any confining pressure, any nothing on the sides? Okay, constant, but it probably will be easier if we just say that this is going to be 0, right? There are no stresses on the side. We're just letting this solid expand due to the change of temperature. And what we can calculate from here is strain. And that strain is going to be this number is going to go into the other side, and it's going to be multiplied by the inverse of C, which that's called the compliance matrix, right? So -1, the inverse, is going to be D, and on the other side I have 3 beta k delta t I. And since I know that I'm not going to cause any shear strains, probably I just can look at the normal or volumetric strains. So epsilon 11, epsilon 22, epsilon 33, which is just the top of the strain vector, is going to be equal. If you remember, d is, I'm making an assumption here that you could make different if you wanted. You could invoke here anisotropy, but we're going to work with isotropy, so all these diagonal coefficients are the same, and these off-diagonal coefficients are the same too. And you multiply that times 3 beta k delta t, and this is all the same. So all the strains are going to be the same, and they're going to be all equal to, these are all the same numbers, so it's going to be 1 minus 2 times Poisson ratio divided by Young modulus times what I had in this matrix. And you can further work with this. Do you remember what is the bulk modulus in terms of Young modulus and Poisson ratio? It's exactly this. It's Young modulus divided 3 times 1 minus 2 Poisson ratio. So I can modify this equation and write this is going to be k minus 1, and this k minus 1 inverse of k times k is going to be 1. So this is going to be minus beta delta t. So if delta t is positive, which means heating, then we get an epsilon 11 which is negative. So heating leads to dilation, and cooling leads to contraction. Makes total sense. We haven't discovered anything new, but what I wanted to show and make emphasis is that this same linear coefficient, and it's called linear because usually you just do it in one direction, this linear coefficient of thermal dilation is, in order to put it into our 3D elasticity equation, has to be accompanied by a 3 over there. Sometimes that's not clear in many books. In many books you may find all of that as a dilation coefficient, but the linear dilation coefficient is this one, and if you want to put it into a constitutive equation like that one in 3 dimensions, you have to put a 3 in front of it. But it comes from there. Actually, the actual definitions comes from here, and you can work this out to get over there. But I just went the other route, which is a little bit easier. So let's try to get a grasp about what these changes can cause. In rocks, beta usually goes from 1 to 10 to the minus 6 to 10 to the minus 5, 1 over Kelvin. And if we imagine, for example, a huge change of temperature that we could have of about, say, 100 degrees C or 100 degree K, which is the same, you can have strains, linear strains, which are in the order of 1/10,000 to 1,000, right? So, for example, here, minus 5 plus 2 will give you minus 3. and that will give you a linear strain about 1,000. It looks very small, right? 1,000 of a strain. It seems that it's not much, but actually it is quite a large strain. For example, with waves, sometimes you have very small strains, 10 to the minus 6, 10 to the minus 7, 10 to the minus 5. 10 to the minus 3, especially for rocks, is very high. Probably for soils, it's not a lot. But for rocks, this strain can cause significant changes of stresses. And that's what we're going to see right now. So let's do now an experiment of constrained dilation. In an experiment of constrained dilation, I'm not going to let the solid expand as I change its temperature. It's the same equation as before, but now I'm saying no strains, because strain tensor is going to be equal to 0. That will be equivalent to putting this solid in a box, very stiff box, that does not let the solid expand in any direction as you change the temperature. So what are we going to get now? We know that it's not going to dilate, it's not going to deform, it's not going to change size, but instead we're going to get, what do you think? So before we get these two, it's a thermal dilation. Now, what do we get? We get a thermal stress, or a thermal, if you increase the temperature, it will be a swelling stress. And its value, it's straightforward from this equation. It's just 3 beta k delta t. Again, we don't have shear strain terms, so I'm not going to write those. So let's, for the same exercise that we did before, let's try to calculate what is going to be the change of stress that we could produce by applying a change of temperature. So notice again that if we have a positive change of temperature, and that leads to a positive increase of sigma 11, which means compression, we have a negative change of temperature that leads to tension, which makes sense with our assumption. So let's say that we have a bulk modulus which is about 10 gigapascal.